Hi folks, welcome to this second video on proving trig identities. As we go through this material, I think it's important to have a look at that formula sheet. And you can find this in the video description. There's some stuff that we don't know yet. There's some stuff at the top that we do know about trig. And then down at the bottom there are the definitions of cosecant, secant, tangent, and cotangent, and the three forms of the Pythagorean identity. When we're working to prove a trig identity, there isn't a single approach that I can show you. I can't tell you how to prove every single one. Each one is its own little logic puzzle where you try and make the left side equal to the right side. But I can give you a toolkit of stuff to go through, or sort of a checklist of things to try out. So here are three things that I think about a lot when I try and prove a trig identity. Can I bring everything down to sine and cosine so that I have fewer trig ratios involved? I think about, are there opportunities to use the Pythagorean identities? And the one that is really clear in my mind is this one, sine theta plus cos squared theta equals 1. So if I see a 1 and a cos squared theta, or a 1 and a sine squared theta, I often think, hold on, are there opportunities there to use a Pythagorean identity? And would it be helpful? The other things I look for are algebraic operations, like factoring. So try it if you can. If you can factor something and it looks like it might help to divide something out, try factoring. Greatest common factor and difference of squares and trinomial factors. Using common denominators. So when are we going to use common denominators? We're going to use them if we want to add or subtract fractions. Other things I might think about are multiplying by 1. So there's a bajillion ways to multiply by 1. You can multiply by -1 over -1. We've seen that in the last video. The other thing that might help for multiplying by 1 is multiplying by conjugates. So conjugates are pairs like this, a plus b times a minus b. And what they really are going to do is change the look of a denominator, or possibly a numerator. But that's when I tend to use them, is if two things are allegedly equal, but their denominators look very different. They often let us use a Pythagorean identity after the fact. If I have fractions that have multiple numerators and just a single denominator, you can split them. So a plus b all over c is equal to a over c plus b over c, if that happens to help. And then finally, expand expressions. So if I have something that can be FOILed out or distributed, then I will. And I'll sort of go down this checklist and see if there's anything there that might help me. Now, I might try a thing and it doesn't help. It may send me to a dead end. And that's okay. That just means that we tried something, it didn't work, we'll go back and try something else. In this video, I'm going to walk you through my thinking process for proofs of these 6, and also there'll be a secret 7th one at the end. But there are often many ways to prove a trig identity, so it's okay if you have a different way, but I'll walk you through what I'm thinking as I see each of these. So my job is to prove that these two sides are equal. And I'm going to look at it kind of with an open mind and say, well, what are the problem areas of this? I think what's unpleasant on the left is that you have two separate fractions. I think what's unpleasant on the right is that you have one of the dark trig ratios. You have secant. So the two things I'd be looking to do are put those fractions together. Okay, now let's go up to our techniques. If I want to put fractions together, I probably need a common denominator. So let's build one here. We're going to have to multiply this first one by 1 plus sine x over 1 plus sine x, and the second one by 1 minus sine x over 1 minus sine x, just so that they each have the same denominator of 1 minus sine x times 1 plus sine x. Now, it's true that I happen to be using conjugates here, but it's really just for the sake of making a common denominator. So I'll multiply that all through. On top, I'll get 1 plus sine x. On the bottom, I'll get 1 minus sine squared x, because they multiply out. And as I multiply through, I'll get 1 times 1 plus sine x minus sine x. Oh, those are gone. And then minus sine squared x. In the other one, I'll get 1 minus sine x up top, as I just multiply that 1 by each of these. And on the bottom, I'm going to get 1 minus sine squared x. Okay, so I do have a common denominator. The right side, I don't love the fact that it's got secant involved, so I'm going to rewrite that as 1 over cos squared, just in the hopes that that will be something more helpful or easier to deal with. I don't have to do that. Again, there are many ways to prove this. Now that I've got a common denominator, I can just add my numerators. Okay, so 1 plus sine x plus 1 minus sine x. Oh my gosh, so on top, that's really just 1 plus 1 makes 2. The sine x is added to 0. And I look like I'm really close here. On the right side, this is the same as just 2 over cos squared x. And now's the point where I say, okay, how can I turn that 1 minus sine squared x into a cos squared x, or vice versa? Well, I might be thinking about my Pythagorean identities here, because I have a 1 and a sine squared involved. The basic Pythagorean identity is sine squared theta, or sine squared x, plus cos squared x equals 1. And if I rearrange that, if I move the sine squared to the other side, I get this. Cos squared x equals 1 minus sine squared x. So this whole thing right here on the bottom must be equal to cos squared x. And by manipulating both sides, I've made the left side equal to the right side. There's one way to prove it. So to recap, the things that I noticed here is I've got separate fractions. I want to add them. Common denominator. Okay, common denominator. Change to sine and cosine. And on the left, I just kind of followed the algebra for a while, and then I ended up using Pythagorean identities. All right, next one. We've got two fractions that are allegedly equal to each other. We need to prove how. So I look at this. There's nothing to factor. Everything's in sine and cosine already. And there's no Pythagorean identities to use because there's no sine squareds or cos squareds. I just want to change the look of a denominator. And if I look at my things to consider, changing the look of a denominator is often something that conjugates can do. So I could actually work with either side here. I'm going to choose to turn the left side into the right, but you could do it the other way around. And so I'll just try this. I'll try multiplying by the conjugate of 1 plus cos x, which would be 1 minus cos x. And if I multiply through here, I'm going to get sine x minus sine x cos x. Turns out it would be actually better here to not bother to multiply it all out. But I'm going to pretend I don't have that insight and figure out what the bottom is. Okay, so from here I can think about what is fishy about the bottom. Again, sine squared plus cos squared of x equals 1. So if I built a 1 minus cos squared, that would be equal to sine squared. Okay. So the bottom of this fraction on the left is just sine squared. And on top, I could factor it. And maybe, to begin with, you didn't actually multiply it out. Maybe you left it like this. At this point, you can see these divide out. What are we left with? 1 minus cos x all over sine x. Left side equals the right side, which is what we wanted to demonstrate. So in this one, we wanted to change the look of denominators. We used conjugates. You could just as easily have used the conjugate 1 plus cos x on the right-hand side and turn the right hand into the left hand. That would have been fine. In question 3, we have kind of the same problem. We want to change the look of the denominator. On the right side, you really have a denominator of 1. And if we had it as a denominator of 1 minus sine x, that might help us figure this out. I can think of at least 3 ways to get started on this. You could use a conjugate on the left, you could use a conjugate on the right, or you could start by using a Pythagorean identity on the right-hand side. That would be a little bit weirder. If it were my money, I'd probably just try and create that denominator of 1 minus sine x on the left-hand side. And the way I can do that is by timesing by 1 minus sine x on top and bottom. Okay. It happens to be the conjugate of the numerator too, but I'm really just trying to build that same denominator on the left and right. Let's see what I get. I get 1 minus sine squared x all over 1 minus sine x, which is close. And then the top of that looks very fishy. It looks like sine squared x plus cos squared x equals 1. Okay, so 1 minus sine squared x would just be equal to cos squared x. And so I can write that on top. Cos squared x all over 1 minus sine x. Left side equals the right. I created the same denominator on the right and left. And sometimes if you really want to, you can just try and create the same kind of mess on both sides. Again, this isn't the only way to prove this, but it's a way that deals with your issue, that they kind of look different on the denominator. Okay, here comes another one. We've got tan x times cos x plus cotangent x is allegedly equal to the simpler expression of sine x plus 1. If I ask you to graph what's on the right, no problem. If I ask you to graph what's on the left, very confusing. So when I look at this, it has so many trig ratios, I would be inclined to use the first suggestion, which is bring everything down to sine and cosine. I'll rewrite tan as sine over cosine. Cos x is just cos x. Cotangent is cosine over sine. And I'll just try and turn it into what's on the right side. Now, if we want to multiply this through and be really clear about what's happening, that's a cosine over 1. So if I multiply this in, I'm going to get sine x cos x over cos x times 1, which is just cos x. If I multiply these ones through, I'll get sine x cos x over sine x cos x. And then we can see what divides out. So you can see in that first one, those cos x's divide out. In this one, everything divides out. What are we left with? Sine x plus 1. It's okay with me if you skip straight from here to here, from the second step to the last step. But at some point, we're probably going to need to go to sine and cosine. Somebody might do it differently. They might define cotangent as 1 over tan and leave that tan as tan. That's okay for a little while in this question, but eventually you'll have to go to sine and cosine. Moving on, we've got this one that is already all in sine and cosine. There's no Pythagorean identities to use because there's no sine squared or cos squared, at least not yet. There's nothing to factor. There's no fractions at all. I think the only thing we can reasonably do here is expand these binomials. Okay? And you can write them out as their times by themselves. It might be worth at some point learning just the basic formula that a plus bl squared is the first thing squared plus 2 times the first times the second thing plus the second thing squared. Similarly, for a minus bl squared, it's going to be a squared minus 2ab plus b squared. So in this first one, we get cos squared x plus 2 sine x cos x plus sine squared x. In the second one, we'd get cos squared x minus 2 sine x cos x plus sine squared x. Okay, and if you're not sure, then you can just write those brackets out twice and FOIL them out. You'll get to the same result. And one thing we notice here is that 2 sine x cos x and minus 2 sine x cos x, they add to 0. So let's just collect our like terms. We have 2 cos squared x plus 2 sine squared x. Okay, like terms. And you probably have an inkling that this just makes 2. A proof, though, is telling the story of why it's true. So we can take out a common factor of 2 here and recognize that what we're left with is sine squared plus cos squared, which is the Pythagorean identity. This here is just 1. So we have 2 times 1, or just 2. Left side equals right side. Expansion helped us find those like terms, and clearly the number 2 is easier than the expression that we started with. This sixth trig identity has a lot of different ratios in it. It has sine, cosine, tangent, and secant. So if it were me, I'd be looking at that first suggestion that says bring everything to sine and cosine, especially since in the end it's supposed to be just sine. So I'm going to work on the left-hand side, and I know that secant is 1 over cosine. And that would be all over tangent, which is sine over cosine. What we end up with here is a nested fraction, or sometimes it's called a complex fraction. There are a few ways to deal with them, but the main thing is not to freak out, not to get too worried. It just happens to have fractions within fractions. That's okay. We're going to try and deal with whatever we have. We end up with a bigger mess in the second step than we did in the first, but hopefully it will help us out. When I look at the top, I got 2 things, 2 fractions that I want to add together or subtract off. To do that, I need a common denominator. So I'm going to have to times this little fraction up top by cos x over cos x. And that's going to give me, on top of the little fraction, 1 minus cos squared x all over cos x. And this is all over sine x over cos x. Okay, that does look pretty messy here. I think it doesn't have that many signs in it. I also think it's really fishy that it has a 1 minus cos squared x. And you're going to get used to just knowing what substitution that is the more that you do these. But let me try that Pythagorean theorem, or Pythagorean identity rather, and try and rearrange it. Oh, it's sine squared that's equal to 1 minus cos squared x. So I can make that little substitution. Going back and saying, okay, how can I use Pythagorean identities? And so this is what I have, which you may not be that happy about. It looks complicated. I think at this point it's worth taking a little trip down memory lane on dividing fractions, because they're really not that bad. What if we had, I'm just going to think about it over here, 2 over 3 over 4 over 5. That would mean 2/3 divided by 4/5. Well, we actually know how to divide fractions. We multiply by the reciprocal, okay? And that would give us 10 over 12. So even though we may not like the look of nested fractions, they're not that bad. This thing that we've got over here just means sine squared x over cos x divided by sine x over cos x. In other words, it's sine squared x over cos x times the flip here. Cos x over sine x. And once we write it like that, these can divide out, and we end up with just sine x. So the left side equals the right side. If you have other tricks that you like to use with nested fractions, that's okay. But in the absence of any sort of special insight, we just deal with them. We just say, okay, we've got fractions within fractions. Eventually I'll divide. I'll do as much simplification as I can first. That all brings us to the secret 7th trig identity to do. And it's about dealing with nested fractions as well. So if you want to pause the video and see if you can get started, maybe make a first step, It's okay if you don't make it to the end, but see if you can do sort of the next reasonable thing. When I look at this, I think there are too many trig ratios. There's literally everything except sine in this. So I would like to bring it down to just sine and cosine. So tangent is sine x over cos x. Cotangent is cos x over sine x. This is the definition of cotangent that we'll use more commonly. And this is all over cos x. On the left-hand side, I would be thinking cosecant is 1 over sine x, and secant is 1 over cos x. So the whole thing together would be 1 over cos squared x. And then I have a bigger mess than I started with, but maybe it's one that I can start to play with. I'm going to try and make common denominators on the top here. So that's sine x that I'm multiplying this first one by, and cos x that I'm multiplying the second one by. So that up top I'll get the common denominator of sine x over sine x cos x rather. Okay, so what will that give me? On top I'll get sine squared plus cos squared of this denominator of sine x cos x all over cos x. And on the left-hand side, I've got 1 over sine x cos squared x. This is looking somewhat promising at this point. Again, if you have tricks here for dealing with the division in the left-hand side, go for it. But what I notice next is that sine squared plus cos squared. Oh, that's fishy. So sometimes you have to sort of look back, take a breath, look at it, say, is there anything here that's obvious? Yeah, sine squared plus cos squared is just 1 over sine x cos x. That is all over cos x. And the left really means 1 over sine x cos x divided by cos x. Or divided by cos x over 1, you could say. And if we want to divide fractions, well, we just flip and multiply. So we get sine x cos x on the bottom here times 1 over cos x. Dividing by cos x is the same as multiplying by 1 over cos x. And what do we get in the end? On the bottom we'd have sine x times cos squared x. Oh my gosh, the left side equals the right side. We have proved what we set out to do by manipulating both sides. If you really wanted to just work with the left, you could. So in the video description below, you'll find a worksheet from Math Power 12. And you could do some questions from 1 to 20 and from 26 to 33. I've attached work solutions that show like a way of doing each of the proofs that are given, but there are often many, many ways that you can prove an identity. So if you do something different that also leads to the left side equaling the right side, then congratulations, you found a different proof, and that's fantastic. As you go through your work, check out the formulas, which are also in the description below, as well as this handy slide that gives you things to consider or techniques to maybe try as you're trying to prove an identity. There's both blank and filled in notes in the video description below. Since they're all little logic puzzles, I assume that some of them will go smoothly for you, and some of them will cause us some grief. There'll be help available in real time, so please make use of that. And maybe spend, 20, 25 minutes on these today, and spend some more time on them tomorrow. I hope this has been helpful. Good luck with the material, folks, and take care.